Welcome again to another webinar from LD Didactic. My name is Eduardo Dalmolin. I'm Area Sales Manager here at LD. Today I have with me my colleague Dr. Vitsky. He's our expert in the field of physics. And the topic of today's webinar will be computed tomography with our CT module from LD and the X-ray machine. So without further ado, I will pass the word to Dr. Vitsky, and he will be presenting to you this nice piece of equipment.
Okay, thank you very much, Eduardo. And hello out there. So I'm Carl, and we are talking today a little bit about X-rays and what we can do with computed tomography and how easy it is to set up such a thing and what the results will tell us in terms of physics and where such a thing can be used. As you see here in front is our setup, X-ray machine, computed tomography. Here we have an additional camera that will show you the view from up above into the experiment chamber later. And so now I would like to start with the first sheet. And yes, the question is, how is a computer tomogram made? And as a joke, how many nuts are in a chocolate bar? And so what we are talking today is X-rays. It's just the season of Nobel Prizes. And you all know it was 1895 when Röntgen discovered the X-rays. And about half a year later, the company Leibold already has sold the first X-ray tubes. And these are ones of the first commercially made. And the hand you see on the left hand of the screen is the hand of one of the workers in 1896. On the right hand side, you see today's setup. And below it, you see a full three-dimensional view of the chocolate bar we have X-rayed. And you can see there are some nuts inside, there is some structure inside, and we're doing this today, how to make this. In the left image, you can already see the first problem of such an X-ray. In the hand wrist, there are a lot of overlapping bones. And they can't be separated because X-rays pass through it and they will always interfere with one another. So what we are doing today, just a short basics on computer tomography, what is needed for the setup, then we'll start a measurement, have a look at it and talk about some more examples. For time reasons they won't be recorded live, and talk about why and what we can learn from these things. So, CT theory. Well, as I said, X-ray images are just flat projections of everything that's inside the X-ray beam. And stacked items like the bones in a wrist or like all the body organs are overlappingly pictured on the X-ray image. And now how to circumvent that? We can take several different pictures from different angles and hope that we'll get one view where there is a correct detail visible, for example a broken bone. Or we can take more pictures and process them mathematically to reconstruct the full three-dimensional part of the object in the X-ray beam. And for that we need to talk about that every line of sight from the X-ray to every pixel in the detector contains all the information it has been passing through. And for the visualization, andere Kamera, we can, for example, think about several sweets in one box, and everybody, when you try to figure out how much is in there, you turn it. You just turn it around to see it from every side. And this is exactly the idea of the computed tomography. I have an object, rotate it in front of a camera, and then mathematically process all the images together. Maybe you have been to a hospital, and you know in hospital the patient is lying flat on some desk or whatever, and the X-ray tube and the detector is rotating around the patient. In our setup, the X-ray tube and the detector are held fixed in place, and it is a sample that is rotating. So the sample is just rotating around itself, in contrast to what you might know as CT in a hospital, because rotating a human all the way around, upside down, isn't a good idea, especially not if you're lying there with broken bones. And yeah, a very short mathematical, just to mention it, we have this formula you see on the right lower hand, where we have the integral of everything that is absorbing in the X-rays. And the mathematically challenging task is how to reconstruct such an image. And there are words like inverse radon transformation, filtered back projection, that show it is mathematically possible to do a full reconstruction of the 3D volume just from a few pictures of X-rays. And this is only possible since the computers have got so powerful that it can be calculated. It started somewhere in the 1970s, and nowadays even the mediocre laptop is able to do such a calculation. And if you want to visualize it, it's something like all the images taken are back rotated in the rotating system, and they are added up and will give together the image, but we'll see that in a minute. So, right, talking about the X-ray machine, this from my left hand to my right hand is the X-ray machine itself. We are having an X-ray tube here underneath my finger where the X-rays are produced, 35 kV, 1 milliamp. It's not that much, but it's absolutely sufficient to do all the experiments we'll talk about, and for safety reasons everything is shielded here. There is no radiation leaking to the outside. We're talking about microsieverts per hour where I'm right standing here, so it's absolutely safe. There is a locking mechanism, and you hear it when I close the doors. Now the doors are truly locked and the radiation is switched on. You see the cathode is glowing. It's a reddish glow down here. The X-rays pass through my object, which is this red one here, you will see later in detail. And now, for the purpose of recording, we have a thing called computed tomography module. And maybe you can switch off the overlay. One. Okay. And here we see our tomography module, which is the silvery thing here is a camera looking at the fluorescent screen from the outer side. So from the inside there are X-rays passing on the fluorescent screen. You see this black disc here. And from the other side, visible light is emitted wherever the X-rays pass. And so we can take a view from this camera. And so we will have an image like this. This is a long time exposure photographed at night. And you can see how the greenish glow of the fluorescent screen is showing the pocket calculator. And so, to demonstrate this live, we'll put in our pocket calculator, and I'll go just for the software. And here we are with a live image. And you can see what the camera sees right now. Here we have my fingers in front of it. And when I close the door, switch on the high voltage, you can see the image of the pocket calculator on the fluorescent screen. And now I can swap this pocket calculator, which is just a two-dimensional image, for something that is sitting on the axis of my goniometer. So you can see this reddish part of Lego. And when I switch on the X-rays, here you are. You can see it on the lower right-hand side, a view from the top, whereas the reddish part, it's the optical image, and on the main screen from the software, you can see that we have a nice pass-through of the image of the module. And then, now we can start to rotate our sample and take some pictures of this. And this is just what I will start. So the settings have been made in advance. Yes, I want to override it. And here we have now our recording live of a tomogram. So you see on the left, in the middle, on the left side, you see what is being reconstructed in a plane which is indicated on the right-hand side, which is a live image, by some red lines. So we are looking at the inner part of a Lego brick, which is holding our plastic pieces. And if you think of rotating it, and you will see on the left that it is partially reconstructed one by one. And this is exactly what we discussed a few minutes ago when it comes to inverse back transformation. And so what we are seeing here is how the image is reconstructed in real time. There are a lot of rays being shot through the sample, and they are added up and calculated on the right-hand side. And to be mathematically precise, it is not the projections that we are adding up, but it is a logarithm of the projections. And this is then high-pass filtered with a special Fourier transformed filter, which makes it mathematically correct. And so you see on the left, the Lego brick is really good visible, and when I move a little bit downwards and upwards, I get different slices through my sample. Here we have a larger Lego brick, and yeah, that was just 1.5 minutes now, and in 3 minutes this one will be finished, and we can have a look at the 3D details, or we can already have a three-dimensional view right now. And as it is, when the 3D data is inside the computer, I can just rotate around, and visible is here, for example, the inner part of such a Lego brick, and I can cut it. Everything is open now that the data is inside the computer. I can have a cross-section view of it, and so on. Going back to the recording, you see the right top, there is a green bar proceeding, and we've got 1 minute left until every view from 360 degrees is taken. And of course the sample is rotating one complete turn around, so we get a view from every direction, and all these views are added up to give me the digital image, the digital clone, is so to say. Okay, so it's another 20 seconds. So this is 450 pixel times 450 pixel digitized image, and the reconstruction is 460 to the cube. So we're talking about 500 million of pixels, or so-called voxels in this context. We have little volume elements which are now calculated. And now that we have finished the data gathering, we can go for the three-dimensional image, which is here. And now we can do a little bit of image improvement, playing around with contrast, cutting off noise, and changing the color, changing the lighting, whatever you might imagine for such a computer software. So this is a three-dimensional image of what has been taken into the experiment chamber. So we started with a very simple Lego brick system to show you what we are doing. And now the question right from the beginning was, how many nuts are in a nut? And I will change my sample. First of all, you can see this is what we have just X-rayed. And here you see, should take it like this, quite similar to what the X-rays have seen, with the only difference, the color in red is visible through the camera, and on the other hand, the X-rays can see what is going on inside. Okay, so this was our first object. Second, we played a little bit with a chocolate bar, which is put in a holder inside a plastic glass. And so it is still inside its packaging. Oh, you see the brand. I don't know whether it's common or all around the world, but it's common here in Germany. And now I can put that on the axis of my goniometer, fasten it, close the door, switch on the X-rays. And in order not to let you wait another 10 minutes, we have already taken a sample run on this one, which I will open up in the software. And here you can see this plastic ball put on its holder from the outside. And it's a three-dimensional reconstruction that took approximately 10 minutes to record on the system. And so now I can start to cut through this one. There's a chocolate bar inside. You see all these characteristic wiggles on the surface made of chocolate. And when I cut a little bit deeper into it, there is something that already looks like, it's better visible when I switch off the light. Here you can see 1 nut, 2, 3, 4 nuts. The inner part of such a nut is filled with air, which is low in absorption. And the outer part is shown in red here, having a higher absorption coefficient for the X-rays than all the candy cream around it. So this is mostly sugar and a little bit of water around the nuts. The nuts are made of fat, and they do absorb a little bit more of the X-rays, so we get a nice contrast here to distinguish them. And on the outside, we have the chocolate itself, which is again highly absorbent for the X-rays. And we do not have any other obstacles inside, obviously. And so this was the answer to the question, how many nuts are in there? And the answer is just 4. And well, yeah, so that's a nice picture, but we're talking about physics today. So what do we learn from such an image in terms of physics? And it is much easier to discuss it when we are not talking about nice, beautiful pictures, but we are talking about something we know very well. And just to load another example is called a 3D phantom. And that's I'm going to switch to. Okay, unlocking the door, removing the nuts. And what we have here is a thing made of white plastic, where you can see there are some tiny wires at the top of it, somewhere here. And below it there are certain layers of this white plastic material where we have some hidden features in between. They are not visible from the outside, so students have to X-ray it to see what is inside. And we have already done, as before, just to save time, a recording of this one. And when I put it on the axis, just like this, we can compare with what the computer screen is showing. And on the computer screen we can now see, okay, it looks like this, no surprise, we have seen that before. But now we can take all the possibilities of such a computer tomogram to measure. We're talking physics, we're measuring things, and let's have a look. And we'll cut off the top layer. And here you see all those tiny wires. Can zoom in a little bit. And now, yeah, you see we have a large diameter wire and succeeding lower diameters, and the last one right here is barely visible. So we have already reached the resolution limit of our CT setup. And now students can start to calculate what is, for example, the dimension of this. It's 2.1 millimeter, but these are just artifacts around it, and the wire diameter is something like 0.5 millimeters. And yeah, you see for the lowers we get weaker images, and when we pass through the disk we have, well, that needs some fine-tuning. Let's make it like this. We have some holes in the next layer. In the top layer there were wires in air. Now it is air inside the plastic material. And what we can do, for example, is cut off a plane for radiography. And now we can go to a radiography and say, for example, create a line profile. And I want to see the line profile along these two parts. And you can see it here. We have a certain absorption coefficient here. And it is dropping where the holes are. But it is not dropping sharply. These holes have rectangular walls. They are just bores. But for the CT, there is already a loss of transfer function. And we got something that looks more like a Gaussian. And now students can export such diagrams or the data and do calculations on the resolution properties. Again, we have a set of large ones, medium ones, and the small ones are barely visible here. They are just tiny dots here, and we can do again calculation on the size and so on. In the next layer we are talking a little bit more about absorption coefficients. And going back to history, this system of computer tomography was developed by a man called Hounsfield, and named after him is a Hounsfield unit, which is a measure for the absorption coefficient. Physics just calls it absorption coefficient to be measured per centimeter, and Hounsfield is more for the medical guys, talking about Hounsfield's units. And in the upper right you can see a display where the computer shows me what is right underneath the mouse cursor. And in this layer we have our plastic material, which is polyoxymethylene in the hole, and we have a patch of air, a patch of polytetrafluoroethylene, Teflon, and a patch of polymethyl metacrylate perspex glass. So they all have different absorption coefficients, and students can take their measurements and see that the Teflon is quite homogeneous in itself, but it is very different from the other plastics. Of course, there are fluorine atoms which absorb more of our X-rays than the pure carbohydrates like plexiglass or polyoxymethylene do. There is nothing but hydrogen, carbon, and a little bit of oxygen in here, and this is pure air with the lowest Hounsfield units and so on. So in the next layer we've got even more to show. That looks strange, and it should look strange. That's exactly the reason why we did it. And it's better understandable if we take a cross-sectional view of the whole thing. And there you can see there is a screw. Just a metal screw with a thread up here, screw head down here, and there is another screw on the left-hand side. So here you can see it. This is metal, and metal is so dense that our relatively weak X-ray of 35 kV and 1 milliamp cannot pass through it completely. So we get the effect that is non-linear. Everywhere else the absorption is not saturated, but here is so much metal we don't know how much it is when we look through it in the X-rays. And as a result, when we turn it by 90 degrees and cut to the plane of these two screws, we see there are two screws. Okay, we can see it from the side, but we can barely figure out what is going on between them two. Here we have a lot of strange structures that are not present. And that is exactly what the people in hospital should remember. For example, a computed tomography of the neck is hard to do or barely impossible if that person has metal tooth fillings. So they are always absorbing the radiation and standing in the way. And they do produce artifacts, clearly visible here. And so the image quality is degraded intentionally. And this is exactly what we wanted to show with this phantom. So in one piece of plastic, oops, should switch on everything. So in one piece of plastic we have collected a huge number of samples to teach it from a physics point of view and not only generate those nice looking colors. Okay, so much for this setup, I guess. We have something that can produce nice pictures, but we have also something that can be used for teaching X-ray and properties of X-rays. One thing I didn't mention yet is the self-hardening. When you take a look at such an image, you see that the rim seems to be a little bit different from the inner parts, which is due to partly absorption of the high energy X-rays on the way, and so on and on and on. And there are quite several instruction sheets, as you know from our company, talking about such experiments and what can be done with it. So now I would like to show. Okay, so I'm here talking about pocket calculator. This is all part of the PDF. So we have a second set of computed tomography. So here we have seen the big one, which is a lower resolution, but using the full area of our fluorescent screen. We do have a second X-ray sensor, which has the fluorescent screen directly attached to the chip. You can see it in the photo here on the right. There is nothing on the fluorescent screen here, but the sensor itself is sitting in the experiment chamber instead of the fluorescent screen. And we have a large 50 × 50 millimeter, which is large for silicon chips, field where we can detect X-rays. Okay, so this one is smaller, much smaller than our fluorescent screens. So the objects have to be smaller too. But on the other hand, it has 48 micrometer of pixel size, which is a much higher resolution than the one I've shown to you right in the last half hour. Taking 12-bit grayscale images is a lot less noise, simply because the setup we have seen with the camera, a lot of light from the fluorescent screen does not get to the lens, of course. Attaching the fluorescent screen directly on a silicon chip will solve that problem. And it is very good for high-resolution CTs of small objects. And this is a bug, just a small animal put on a needle. Okay, it's dead. And the high resolution says it is 8,000 voxels in 1 cubic millimeter we're talking about. So there is a lot of fine details on the legs of this bug and so on. So if you're more into high resolution of small things, this is the one for you. And if you like to teach the basics and can live with a larger volume, with a little bit less resolution, the one I've talked in the last half hour is for you. So now we have a three-dimensional image in our computer and we can save it. Of course, it's an open format. We do not hide the data, we publish it. And the raw format is just a cube of floats. So we have 400 times 400 times 400 data of float, which is around a gigabyte for such a sample. And this can be used in independent software like Drishti or Volview and many others that run around as freeware, open source, whatever you like. So you can probably use one of those, for example, for Jennings STL. STL is nowadays quite common, simple triangles, and lots of them. And it's used in the 3D printer area, so we can have a digital clone of what we have just X-rayed. You can scan it, and then you can print it if you have a digital printer using such software. And in the very end, what have we seen today in the last half hour? So we have seen that just a camera is needed to make a CT setup when we've already got a computer-controlled X-ray machine. We have seen the practical application of such X-rays by identifying hidden things like the nuts in a chocobar. And we have seen teaching absorption properties with a 3D phantom, a well-known thing which is fully documented. And we have all those things like resolution, like Hounsfield's units, the physicists like to talk about and like to teach the students. And remember, this is a completely independent setup. So when you're talking about artifacts and suboptimal adjustment, you don't have to de-adjust your big CT machine, but you can do it with our setup, which is reserved for the students. So they can play around with it without messing up much. And so always a hands-on experience is the best than just showing a video or doing some PowerPoint talks. The real life is always where the students can play with it. For the Mint section, we have this handling and visualizing of 3D data sets. There's a lot more than I can talk about in half an hour. It's about segmentation. So it's the usual problem in medicine. You have a CT of the body and want to know what is the liver or the stomach or whatever. So you have quite similar areas of absorption and want to make an anatomic organ out of it. Or for advanced manufacturing, you can talk about 3D printing by STL files. And if you come across an open day, it's a very nice thing to have a beautiful picture of something people can get in their hands and then have the 3D of it. So then I would now pass on more to the sales microphone.
Dr. Witsky, thank you very much for this wonderful presentation. I thought it was very, very informative, really nice. So if you need more information about both the X-ray machine and the computer tomography module, you can find it in this special catalog that we made available. So at the end of this session, we will share with you the presentation that you have seen, and then you have access to the link and to the QR code to access this catalog, which is specific for this device. So you will find everything that you need to know there. So in the name of LD, we would like to thank you for your attention and for your presence during this session. And now we will close. Dr. Witsky, any final words?
Thank you all for taking part of this webinar. It was a pleasure, and hope you will have a lot of fun with X-ray machines in the future.
That's right. Thank you and goodbye.
Bye.
Take care.